This comment from Sir William Bragg really kind of summed it up for me. The important thing in science is not so much to obtain new facts as to discover new ways of thinking of them. The concept of a liquid salt was completely contrary to everything I'd ever been taught. It forced me to reevaluate the way I looked at everything. And when I did that, when I did not say my professor was always correct and started thinking about things in a different way, then the light bulbs went off and the innovation possibilities came about. It turns out that an ionic liquid literally is a liquid. This yellow liquid is a salt. It's not a solution. It is a pure salt. And you can see water on the other side. One of the innovations for these materials was as solvents. This is ethanol, which is a flammable solvent, so it has a safety hazard. The one on the right is an ionic liquid and it doesn't burn and it has no volatility. All of a sudden we had a way to start looking at different ways of conducting chemistry, because one of the most highly used industrial solvents for separations was benzene. You may have heard benzene has a bad rap. And it's volatile, and at the time we started our work, the release of volatile chemicals into the air was the major pathway to environmental pollution. So we decided that we would start and look at some of these compounds. Let's see. So let me introduce you what any of that has to do with green chemistry. There is a principle of green chemistry which most of you have heard about today, which is that a raw material or feedstock should be renewable rather than depleting, wherever technically and economically practical. So today we hear this about bioethanol, right? We have to get all our fuels from corn. How many of you think that's a good idea? Okay, so I'm speaking to the right audience, because you know, in Alabama, we have made ethanol from corn for hundreds of years, but we don't actually burn it in our cars. So the concept of doing this on the scale they're doing it on in Iowa is actually mind-blowing. But if we look at renewable materials and renewable chemicals, there's one big challenge. Let's take a tree. A tree is made up of 3 natural polymers and a bunch of other stuff, but you've heard of the 3 natural polymers. This is lignin on the right, cellulose and hemicellulose on the left. It turns out that the biggest challenge in using carbohydrates for anything has been that separation, which is too expensive and apparently can't be done. So I'm going to get a different answer than I did for the students, I hope. How many of you ever grew up near a paper mill? Yeah, so we remember. So a paper mill is based upon the kraft pulping process. Alabama used to have the largest paper mills in the world. We have practically none now because they're based on this process, the kraft process, which is incredibly polluting and very smelly with all the sulfur that they put into the air. But that process destroys lignin and hemicellulose to leave cellulose fibers so we can get paper. That process is a destructive process, so you're eliminating 2 of the really valuable polymers because that's what we know how to do. Now, why are ionic liquids relevant? So remember I told you ionic liquids could be used as solvents. I have one solvent application for ionic liquids, and this is it. It turns out that certain ionic liquids will dissolve biopolymers with no degradation or no derivatization. Let's see, I don't have the movie. But the concept is that these ionic liquids can dissolve cellulose. How many of you have heard of photographic film? Oh, see, y'all would remember, right? Nobody knew what that was in class. Photographic film is made from cellulose acetate, not cellulose. Cellulose that has been chemically derivatized to give cellulose acetate. You know why? Because everybody knows cellulose is not soluble in any solvents. Well, guess what? It is now. And so how can we change the mindset of the use of cellulose if all of a sudden we can dissolve it? But it's not just cellulose that's soluble. Lignin is soluble in the ionic liquid. Hemicellulose is soluble. Another polymer I'll tell you about at the end is soluble. Any biopolymer held together with hydrogen bonds is soluble. And so we asked a pretty simple question. If ionic liquids can dissolve all those polymers, can ionic liquids dissolve trees? And the answer is yes. Yes, in fact, they can. And in 2009, we published our first paper where we took pine, we use pine because it's Alabama, and we showed that by cooking it with a certain liquid salt, we were able to get a clean separation of cellulose and lignin. I was amazed by that. Some people were not amazed by that, apparently. But by dissolving a tree, you can solve one of the grand challenges of of a carbohydrate economy. Now, we made a complicated process out of it, but essentially the bottom line to this is that we started with a tree and the ionic liquid, and we did a separation of the cellulose, and a separation of the lignin, and a separation of the hemicellulose. So all of a sudden, we now have a ready stream of 3 natural polymers. So now you can really start thinking about a biorefinery, not an ethanol factory, but a biorefinery where a tree becomes a polymer source, a chemical source, any type of source, any of the chemical needs that you get from a barrel of oil, you probably can get from biomass, if you're willing to pay for it and develop all the chemistry. So I thought this concept was great, and I would take it to the DOE. We solved your grand challenge. You told everybody that the only challenge, the grand challenge, was to do this separation, and we in fact did it. So we sent a proposal, small business innovation grant to DOE, and said, oh, hey, we solved it, here you go. And they gave us $100,000 in what's called phase 1. You have 6 months to prove the concept. I was very confident because we'd already done it. And so I took the money. You have to take it or you can't apply for phase 2. And then I applied for phase 2, which is $1.5 million to scale it up. So we proved the concept, sent in the proposal, everything was great, solved your grand challenge, and we got rejected. Ionic liquids are toxic. Ionic liquids are too expensive. You're doing commodity chemicals, and no one in their right mind is going to have a chemical industry based upon your expensive materials from biorenewables. In other words, we took a step back like 100 years. And nobody remembers economy of scale or how you start or how to get your supply or how to build markets. Everybody seems to have forgotten that. So I'm going to give you my refrigerator story. The people who invented refrigerators are not the people who delivered the block of ice to put in the back of the ice box to keep things cool. And if you invented a refrigerator and you went to those people, they would say, no way, your refrigerator costs $1,000, my block of ice costs $0.25. You won't be cost competitive. But it gets worse. They'll say, and not only that, I took your refrigerator. I stuck it in the back of my icebox and it didn't cool anything. That's what we face today. And we have to find a way to get around some of these things. So I started thinking, okay, I can play this game. I'm not just a professor, I'm going to be an entrepreneur now. I need a better business case. What can I do so that they can't stop me? And then I started thinking, okay, I'll take you on industry, chemical industry. What if green chemistry is not just about making things non-hazardous? What if it's about eliminating chemistry and the chemicals industry? I actually published this article in Chemical and Engineering News. I got a lot of interesting comments. But think about what's happening with the chemical industry today. Even my neighbors understand now that plastics might be a problem. When you have plastic oceans out there, you have fish that have plastics all through them. You've got Pacific islands that have never seen inhabitants, and they're covered in all the plastic, which is washing up on the shore. And this is the water bottle analogy. So can we eliminate the water bottle and synthetic polymers entirely? So I said, okay, instead of using renewables to generate chemicals, so you can continue to use chemicals, why not use the renewables and just make the products directly, and therefore eliminate all the supply chains and all the problems with everything else? Now, of course, y'all know this is not as easy as it might sound, but it's not impossible if actually somebody would try and to make some of these things happen. So I think that we have the planet, the tree, the feedstock is incredibly abundant. It should be possible to make every material that mankind needs from a tree or a grass or a crustacean shell, if we think about it and we take it as a challenge and try to get it done. I can give you a cellulose story just to give you an idea of the magnitude. Cellulose is the polymer we hear a lot about. Bioethanol is being made from it. It's everywhere on land, all this lignocellulosic biomass. But do you know how much is actually produced by nature in a year? Let me try it this way. Imagine, if possible, that you could combine the output from every chemical industry in the entire world, every chemical producer in the entire world, and you could sum up all of the mass of all chemicals that they make. And then I would, for a year. And then I would ask you, how long does it take nature to make the same mass of cellulose? You heard my talk this afternoon, don't say anything. The answer is 2 days. 2 days. So imagine how underutilized that resource is. And we are not using it. Instead, we're still getting that oil. So that natural polymers, this is cellulose dissolving in an ionic liquid. I might need another laser, that other laser pointer. Do you still have it? This one is dying. It's because it's red. Thank you. I'll see if I can do this. This is going to be a challenge now. Oh, it's blue. Okay. That is cellulose dissolving in